Okay, so we've heard that there are different schools of Buddhism and different interpretations of quantum mechanics, and something else that is becoming apparent here is that there are different schools of PowerPoint presentations. So you'll see mine will be a definite contrast with Ian's. But anyway, I think variety is the spice of life. So Howard Wiseman, I'm at Griffith University, the same as Aria, which is here in Brisbane, Australia. So we're in the Centre for Quantum Dynamics, and also in the Centre for Quantum Computation and Communication Technology, which is an Australia-wide centre. So I guess, one point to make, which came up this morning, is that half our time we spend attempting to do something useful, working on theories which will help us make better computers and better communication, using some of the deep ideas in quantum mechanics which are starting to come out. And the other half of the time we think about how crazy it all is and try to make sense of it. Okay, but in my talk I'll be talking about the latter part and hope you find that interesting. Okay, so there are three parts to my talk. So it's a history. I'm going to be going back almost a century of history in quantum physics, which is really necessary to tell a story to where we get to where we are today on this topic of quantum non-locality. So beginning with Heisenberg and Bohr and the Copenhagen interpretation, which has been mentioned a number of times already. Then I'll talk about Einstein, which I'm sure everybody's heard of, and his challenge to the Copenhagen interpretation. And then something that probably most people haven't heard about, which is Bell's theorem and the experiments related to that. So that's a very important topic that I'll get to in the latter part of the talk. Okay, so the Heisenberg and Bohr, so I'm going to begin with Heisenberg. So Heisenberg was one of the very young, amazingly young physicists who invented quantum mechanics, the theory of quantum mechanics in the 1920s. And so when you see these speech bubbles, these are not the real words of these people. These are the words that I'm making up to explain in simple terms what they did and what they were thinking. Okay, so this is a picture of young Heisenberg around about 1925 when he came up with his theory. And here he is talking. So he's saying, by thinking hard about the emission of light from atoms, which is something that Ted talked about, and I think in fact Ted had exactly the same picture that I do here. By thinking hard about the emission of light from atoms, I realized that we have to give up the idea that physical quantities like position or speed have definite values for microscopic particles. And it says, and I made this insight mathematical. So that's a crucial thing, that he's not just thinking, oh, if we do this, that'll solve all our problems. It's no, this is a starting point, and then we have to develop a mathematical theory of what that really means, something very precise. By doing that, he says, now we can use it to derive properties of atoms like their quantized or discrete energy levels, again, as Ted talked about. So the idea is there's a lot of mathematical formalism behind this, which none of us are talking about because it's too complex to explain, but I just wanted to emphasize that. Okay, so the idea is that when we have this formalism, we don't have to have pictures like this anymore. We can actually churn through a lot of complicated maths and get out very precise predictions of the emission of light from atoms and infinitely many other phenomena which have now been observed. Okay, but here we're interested in the philosophical implications. And so what Heisenberg thought about the philosophical implications is that all his theory was telling us was the possible values we may find if we measure a quantity. Okay, so giving up on the idea of quantities having values, but we can still talk about what happens, we have to talk about what happens if we measure a quantity, and the theory will then predict the possible values, as Ian mentioned, in that situation. But going on, what Heisenberg's saying, my theory also tells us that some measurements are incompatible. Okay, this is a very important point. For example, if you measure position precisely, then a speed measurement will give a completely random result, and vice versa. Okay, so this was something that I sort of assumed that other people would have talked about already at this time in the conference, but they haven't. So this is just a reminder for me to talk more about that. So I thought that the elephant story, the elephant and the six blind men, which Ken Po Choang talked about this morning, is a very good analogy to use in this situation. So you could imagine a quantum system is like an elephant, well, or what might be an elephant, but we're in an even worse situation that we don't have six blind men who are simultaneously touching the elephant. What we have to do is make a choice, okay, which of those six blind men do we want to be? Will we be the rope man, okay? If we're the rope man, okay, then we go in and we grab around and we say, oh, here's the rope, okay? Which we might, okay. Or are we going to be the pillar man? And if we're the pillar man, we go in groping and say, oh, here's the pillar, okay? Or the wall man, okay? Then we go around and say, oh, this is where the wall is, okay? So every time we do that, we find out something definitely. We find out where is the wall, or where is the rope, or where is the snake, okay? But we cannot even simultaneously do all those things at the same time. We can only do one of those things at the same time. Of course, we could prepare the elephant, okay, prepare the quantum system over and over again and go in and sometimes measure one thing, sometimes measure another thing, and we might get the vague idea that what we actually have is an elephant, but we can never see the elephant all at once. We can never see all of those aspects at the same time, and so one can question whether there is really an elephant there at all. Okay, maybe when we choose to look for a rope, maybe the rope is all that there is there to be found. And if we choose to look for a column, maybe the column is all that is there. Okay, and it's our choice of what to measure. Well, I'm getting ahead of myself. Okay, I'll come back to that. So the other thing I wanted to say, just how can it be possible? Why can't I just go in as the rope man and look for the rope and then come away and come back as the wall man and measure the wall? And the answer is something that Aurea talked about in her talk, is, and Ian briefly mentioned too, is this idea that measurements disturb the system in quantum mechanics, and that this is something fundamentally different from classical physics. So in classical physics, we can make the disturbance caused by our observing something as small as we like, really. But in quantum physics, we really can't do that, because the systems we're looking at are so small. There's a minimum size to the amount of interaction you can have with that system, and that inevitably means when you measure something, it disturbs it. So for example, so I have these pictures here. So these are pictures of wave functions, which you've seen before. So for example, if we prepared a wave function like this, with a single peak, which is similar to something that Aurea showed in her talk, if we then measured the position of that particle, we would almost certainly find it to be roughly here, and after we make the measurement, the shape will not be very much changed. It will have changed a little bit, but not too much, okay? But what if we wanted to know the speed, okay? If we measured the speed of this wave function here, we would get a definite answer. Anytime we measure something, we get a definite answer. Okay, we never make a measurement in the lab and the device just says blurry, oh, I don't know. Okay, we measure, we get a definite answer. So if we measure the speed of this particle, we get a definite answer for the speed, but then the wave function will be completely changed. It will be changed into a wave function that looks something like this. So that if I then come back and measure the position, I don't get the position that I would have got the first time. I get a more or less completely random position. Okay, theoretically, if I measure the speed exactly, this goes on forever. Okay, it spreads over all space. Okay, so I would get a completely random result from that. So I have to choose. If I want to know the position, I can measure the position. If I want to know the speed, I can measure the speed, but I can't do both. Okay. So what Heisenberg and his older colleague Bohr made of this, they got together in Copenhagen around 1926 and 1927 to try to make sense of what this theory meant. So their conclusion, I'll just read what Heisenberg's saying here, is that before a measurement, the property, any property, has no value. Okay? It is the act of measurement itself which creates the measured value. So going and looking for a rope creates that there's a rope somewhere, and you find out where that rope is, but it's your choice of what to measure and doing the measurement which creates that value. And Bohr said even more, so this means the quantum world is not real like the everyday classical world is, the world of tables and chairs and things like that. Okay? And Bohr went on, we should not try to understand the quantum world in classical terms. We should just accept what the theory predicts for our measurements. Okay, so he's basically saying give up on trying to understand the world the way we always have in physics, throw away those hundreds of years of physical theories. We're just doing completely different now. We don't try to understand the world. Okay, so that was a pretty radical thing to say. And not surprisingly, not all physicists just said, okay, that's the way things are now. No, a lot of physicists were unhappy with this, and the most famous one who was unhappy with this was Einstein. And so he challenged this interpretation, so he challenged it in a number of ways, but the way I'm going to talk about is the one that is relevant to non-locality, as we'll see. So here's Einstein and Bohr having a discussion at a conference in 1927. So Einstein is saying, I can't accept the way measurements create reality in your interpretation, Bohr. Physical quantities must have values prior to measurement. Bohr says, why do you say that, Einstein? What's wrong with our interpretation? Einstein, well, for a start, it has instantaneous action at a distance. Okay? And this contradicts my theory, Einstein's theory, of relativity, which says that nothing can go faster than light. So understandably, Einstein was quite attached to his theory that nothing can go faster than light, and he didn't really like what he saw here. And he's just saying, let's go for a walk, and I'll explain. So here they are. Okay, so this is a thought experiment. So this, at the time, this experiment had not been done, but still they could talk about what would happen if you did this experiment. So Einstein's saying, say you have a wave function of a single particle and it's split into two parts which become well separated. So this is exactly what Anil was talking about in his talk with a beam splitter and a single particle coming here. This blob is meant to be a wave function, okay? So it comes in here, goes on the beam splitter and then splits into two parts. So one part is going to go to Bob and one part is going to go to Alice up here. So remember, just as in Anil talks, there is only ever one particle. So there's only ever one particle, and the particle can't be split. Okay, so this is what we end up with. So this is a single wave function, but split into two parts. So it's a single particle, but there's one blob of the wave function here and another blob of it there. Okay, so Einstein's saying, so Alice and Bob are going to then just look for the particle with a particle detector, okay? And say the particle happens to be detected by Bob rather than by Alice. Then in your theory, in Bohr's theory, the wave function has to instantaneously collapse to where Bob is, okay? So what happens, if Bob detects it, then it collapses to a peak, this really localized wave function at the position where Bob is. But more than that, what has to happen over here is that Alice's wave, this wave packet, this part of the wave function over here has to disappear. And it has to disappear exactly the same time that this detection happens, because it has to happen this way to make sure that Alice can't also detect the particle. Because if the wave function stayed over here, there'd be some probability for Alice to detect the particle as well, but then you could end up with both Alice and Bob detecting the particle, which can't happen because there is only one particle. So instantaneously, Alice's part of the wave function has to disappear. So this happens faster than light, okay? So it happens at exactly the same time as this collapse here, which is faster than it would, less time, because it's zero time, that's less time than it would take for light to get from here to here. And according to Einstein, nothing should go faster than light. No information like that should go faster than light. Okay, so Bohr's a little bit puzzled. Are you saying that quantum mechanics is incorrect? He asks. And Einstein, no, just that it's incomplete. He says it needs a theory of microscopic reality to complete it. And there was some other term that people were using this morning that I thought, I can't remember what it was. Anyway, something properties, inherent properties? Intrinsic properties. Okay, yes. So you could think of this as being like the particle has to have intrinsic properties, which is not what is the case in Bohr's theory. Okay, so what Einstein had in mind was that in addition to the wave function like this, there would be an actual particle, this little blue thing here. Okay, and the reason that Bob is seeing, okay, so that the particle must have a position before it is detected, then you don't need a collapse. Okay, then you can still have these two parts. You have, but over here it's an empty wave, and here it's a wave with a particle in it. And there was a perfectly local explanation for why Bob sees the particle and Alice doesn't. It's just because this is where the particle is. So this is Einstein's idea about how quantum mechanics needed to have things added to it, in other words, to make it more complete to get around. So here he's saying, so now do you see the non-locality problem with the quantum theory? If the particle doesn't have a position before it is detected, then you need an instantaneous wave function collapse, a faster than light action at a distance, which for Einstein is unacceptable. Okay, but Bohr wasn't that impressed by this argument. He's saying, I don't think of the wave function as a real thing. So this non-local effect of yours, this instantaneous collapse, doesn't really worry me. In particular, this effect, this non-local effect, doesn't let us send any messages faster than light. Okay, so that's something I'll come back to. Alice is not, or Bob, by the fact that Bob detects a particle, doesn't actually let him send any signal to Alice faster than light, even though the wave function there is collapsing instantaneously. And moreover, oh, sorry, and there's your translation. Moreover, Bohr's saying, also, your suggestion for completing quantum theory only works for a single particle. Okay, the picture I showed was only for a single particle, but basically that was where it was easy to see how it worked. But Bohr is saying, but you don't have a local theory of microscopic reality for all quantum systems, do you? And Einstein has to admit, well, no, but I'm working on it. Okay, so the next major development in this story was in 1935. A number of things happened here, but I want to concentrate on what this physicist Erwin Schrödinger said. So he's also, so you've heard of him before, he's the one who the equation for the wave function is named after, that's the Schrödinger equation, so he's also very important in the development of quantum theory. But yes, in 1935 he wrote some very important papers on the interpretation, in which he said this, more or less. Like Bohr, I don't think Einstein will succeed in finding a local theory that will work in the sense of reproduce quantum predictions, be empirically adequate, okay, for systems of more than one particle. And the reason for that is that quantum theory says that two particles can share a single higher dimensional wave function, okay? And that's not something I'm going to explain. I don't think it's something any of us are going to explain. So you just have to accept that, okay? A single high dimensional wave function, even when they are far apart. And this is something I call entanglement. So that was a term that Schrödinger introduced in 1935. And he's saying what this means is that measuring one particle instantaneously affects the other one. So it's like Einstein's action, but this one is going to be the collapse of the wave function, but this one is going to be harder to explain because it involves two particles. Okay? So Schrödinger is saying, it seems unlikely to me that a complete, inverted commas, quantum theory with microscopic reality or hidden variables, that's another term that we use in physics to describe this, adding extra variables that are not needed in the theory to obtain predictions, okay? That it's unlikely that a quantum theory with these added hidden variables, as Einstein suggests, would solve the problem of faster than light, so FTL, faster than light. Faster than light action at a distance with entangled particles. So he didn't have a proof of this, he just had a feeling that this was not going to be possible. All right. And then I think probably something went wrong there, but we get to the last part, which is the contribution of John Bell. Okay. All right, so I use that as a trigger to remind me that to tell you I'm going to talk about a theorem and then I'm going to talk about experiments. And you might say, well, we've seen lots of experiments talked about and they all seem a bit weird, but what does it actually show? And the point I want to make about these experiments, and I'll talk more about this tomorrow, is that so some of the other experiments are suggestive of certain ways of thinking about the world, okay? But to different people, they could well suggest different things. The Bell experiment is actually an example of an experiment, and there are very few of these, where it lets us say some very definite things about the world, regardless of what we believe. Okay, we don't have to believe in quantum theory. We don't have to trust any of the mathematics, right? We just make certain assumptions about how the world might be, and then we see that the theorem and the experiments prove that those assumptions are wrong. Okay, so as I said, I'll say more about that tomorrow, but I want you to know that these experiments are in a different category from the ones which you have seen before. Okay. All right, so here's John Bell, around about a little bit later than 1964, but here he is explaining what he did. So he's saying Einstein died in 1955, still hoping for a local quantum theory with hidden variables. Like Schrödinger, most physicists assumed it must be impossible, but like Bohr, didn't really care. Okay? But Bell was one of the exceptions. He was the one who did care about what Einstein thought, and so he kept thinking about this, and found eventually in 1964 he found a theorem that Einstein's idea could not work. Okay, so what is a theorem? It's a rigorous proof, okay, mathematically rigorous proof that when he means Einstein's idea, that adding hidden variables to quantum mechanics could not get around the problem of faster than light action at a distance. Okay. So it's a little bit more complicated than the thought experiment I talked about before, because this involves entangled particles. So remember, Schrödinger talked about how Schrödinger talked about entangled particles. Well, that's absolutely crucial here. So Bell's saying my theorem relies on having two entangled particles, A for Alice and B for Bob. Okay, so typically we prepare these by having a source of entangled particles, sending one of them over here towards Alice and another one over here towards Bob. Okay? And so these are two distant experimenters, a long way away from each other. What they have to do is freely choose between incompatible measurements. So remember, that was another crucial idea I talked about before that Heisenberg introduced, the idea that they can choose to measure different things. So Alice has different possible measurements she can choose, which she controls by moving this lever up or down, and we call her measurement choice X. And Bob does a similar thing over here. He can move this lever up or down, and in that way control his measurement Y. Okay? And then they see some outcomes. So it's getting cut off for some reason, but the outcome we're calling A and B up the top there as well, which is just what they read out from their measurement devices. Okay. So for the conditions for a Bell experiment, which at this stage in 1964 is still just an idea, not a reality, the idea was that Alice and Bob must make the choice of what measurement to perform at the same time, and then immediately after actually perform the measurement and get the result. Okay? So the crucial thing is for them to do that fast enough that light would not have time to get from one side to the other. Okay, we'll talk about that. And then they repeat this whole thing many times, each time with a freshly prepared pair of entangled particles. Okay, because once they've made the measurement, then they've got the results. Essentially, whatever quantum state was there is being completely disturbed. No point making another measurement. You'd have to re-prepare an entangled pair and do it again. Okay, so after they've done that many times, then Alice and Bob can get together, and what they do is look at their correlations. Okay, so they do that in a particular mathematical way, but basically they're looking at how often when they chose certain pairs of measurements, so when Alice chose some particular measurement and Bob chose some particular measurement, they look at what their outcomes were, and they look at how often they got a particular pair of outcomes and how often they got some other particular pair of outcomes. They look at all of these things, they do some mathematical analysis, and they work out some correlations. And what Bell's theorem is that those correlations can be really weird. Okay, so here's Alice and Bob saying, wow, that's really weird. Okay, so in particular, in what sense it's weird is that in some experiments like this, the correlations cannot be explained without action at a distance. So there is no local mechanism that can explain the correlations that Alice and Bob get. Okay, so it's important to note, however, that this doesn't mean that they can send a message to each other faster than light. So just like the original Einstein thought experiment, they can't do this. So here, for example, Bob is saying, you know, in any individual run, right, he gets some result here, he makes some measurement choice, he gets some result, but that doesn't tell him what Alice's measurement choice was. He says, I have no idea what Alice's choice was. And if that's the case, then that means there's no way that Alice is actually sending him information. And of course, for Alice, it's the same with Bob, okay? So the non-locality, which I haven't really explained, I've just said that that's what the theorem says, important to know that it doesn't mean they can signal faster than light. Nevertheless, Bell says, nevertheless, like Einstein, I find this very unsettling. And indeed, he asks the question, can nature really be so strange? Okay, because at this stage, as I said, it's just a thought experiment, an idea for an experiment. But not very long after Bell published his paper in 1964, people started working on doing real experiments, and that's continued, well, up to the present day, but I'm going to stop the story in 2015, and I'm going to let Marissa Justina here tell the story about what happened. Okay, so she's a physicist who was in Vienna at the time of the experiment we'll talk about. So since 1973, many experiments have been done showing correlations similar to those that Bell considered, but all of those experiments did not fulfill all the conditions needed for Bell's theorem. But in 2015, there were 3 separate experiments performed around the world, okay, that met all the conditions, and our experiment in Vienna was one of those. So what they did was we created entangled pairs of photons. So you've heard about photons before, you've now heard about entanglement, and we sent them to 2 different labs more than 50 meters apart. So this is the actual picture of the detection device used in one lab, say Alice's lab, and Bob's lab is down at the other end of that corridor there. So 50 meters down there is literally where Bob's lab was for this experiment. And if you're thinking this looks similar to some of the pictures that Aria showed, it's because this is also the inside of a dilution refrigerator, which you need for this experiment as well. Okay, so going on, she's saying in the 2 labs, using state-of-the-art technology, we made random choices for the measurements and obtained the results in less than the time it would take light to travel that 50 meters. And if you know anything about half-fast, like usually we don't notice that light takes any time to travel at all. It seems as if we see the back of the room instantaneously, right? We don't have to wait for the light to come here, but actually it takes a tiny bit of time to come here. And so they had to make the measurements so fast that they could choose what to measure and get the result in less than the time it would take the light to get from the back of the room to the front. Somebody else can do the calculation of how many nanoseconds that is. Okay, so what did they actually find then? So now they've done this definitive experiment. The results showed Bell correlations exactly as quantum mechanics predicts. So yes, nature can really be that strange. Einstein has thus been disproven, okay? Any attempt to explain quantum correlations by hidden variables must involve faster than light action at a distance. Okay, so conclude. So I've talked about these 3 broad stages. The first stage, where Heisenberg and Bohr developed the Copenhagen interpretation, which proposed that there is no reality behind quantum measurement results. Then Einstein came along and pointed out the problem that this seemed to imply faster than light action at a distance, but he thought that you could solve this problem by adding hidden variables to the theory, by making the theory more complete. But then Bell came along a generation later and showed that Einstein's solution could not possibly work. Okay, so it's not just that everything we've tried has failed. No, he proved that there's no possible theory that could actually work. Okay? And moreover, we now know that quantum experiments have verified this, and so quantum experiments defy all local explanations. Now, I haven't explained to you what Bell correlations are, what they look like, and that's because it would just take a bit too long. But I just note that I do have slides prepared, which might be useful in a breakout session or something like that. But for the moment, I'll stop here. Thank you.
So when you talk about sending information, you said that nothing moves faster than the light. But in Buddhism, we talk about consciousness moving faster than light. So what is your take on this?
I guess I'd say I'm not aware of any. Well, okay. I'm a scientist, so if you can tell me what the scientific meaning of that statement is, then I can answer it.
가서나 다처리바가 따제 제제제 배나 로디디 우들란 조가 고소라 어디디 통금면에 혼자 녀야 빠져도 앉아 있는지 지바레스.
So when you say something moves, do you need to see that something? If so, it seems that in science you don't see the movement of the electrons, but you still say that they moves, and you say that you can prove it through he's saying experience. And also when we talk about the movement in Buddhism, we talk this through our experience.
Okay. Maybe let me make one clarification. So when we say, I can't remember exactly what the words I used were, but I think I said nothing can go faster than light. So it's certainly the case that we have not observed anything moving faster than light, but the principle that physicists would believe most strongly in is that we can't send information faster than light. And so that's just a statement about if we look at the experiences of people, if you like, if you wanted to put it that way, who are a long way apart, there's no way that the choices or the free will, the free actions, decisions, whatever you call it, of a person over here makes can affect the experiences of a person somewhere else. There's no way that that influence can happen by any means, like we don't restrict to saying it's carried by electrons or photons or whatever, but just that science seems to indicate that there's no way that that can happen in less than the time that it would take light to go from that event, that decision, to that experience.
진짜 원래 이거로 안에 도투 말했어야지 안에 가서 가르치기 그랬으라면은 안에 내일 코데스지 가르쳐야 되었으나 원래 이거게 뉴르지게 토라 안에 니주탄 투 말했어기 그랬어 인포메이션 세스도 디탄 투 말했어기 그랬어 디 페차샤베면은 그런다 미기 뇨와다 드네케지 시기여서다 뇨와다 드네 잔네시나 텔라 미지 요와체 안에 디키 안에 코란키 안에 자와카리 지비면은 자와디 제베기 슈징기 네주디 안에 텔라 요베기 미니와 찍라 땅구 요베면은 디 네주디 드네 디파톤 로야라 안에 원래 뇨르베기 뇨르세기 토라 딜레 뇨르베기 뇨르세기 토라 도투 마레시아디 안에 세리키 계자시다레스.
My question is, the scientists, they contradict each other, and we get more confused. And my first question is, what is your conclusion? And the second question is, what is the impact or the use of these findings in our day-to-day life?
Thank you. Those are both good questions. So first, maybe I'll make a comment, is that, I mean, science thrives because it is not dogmatic, because people are supposed to engage in rigorous debate about the facts and also about the interpretation of those facts. So the fact that I realize that it is confusing, but it would be dishonest for us as scientists to present things as if we all agree on the way things are, because that's just not the matter of fact. That's not the way things are. And we celebrate that in science, and particularly we celebrate when people change their mind. Unfortunately, Einstein didn't live long enough to hear Bell's theorem, so we'll never know exactly what he would have thought of that, but that's an example. Sometimes you have an idea and you think this is really the way things are, and then somebody proves that you're completely wrong, and you just have to accept that in science. You can't get around that. Now, what was the actual first question? Was, what do I think?
No. What is the usefulness?
Yeah, no, there was another question about what I think. I mean, I said, in regarding what I think, well, I'm not, in my talks, I'm not going to commit, but tomorrow I will talk more about the options, and that will relate to also what Ian is talking about tomorrow. Maybe when we get to one of the panel discussions, I'll be more forthcoming. Okay, what are the uses for this? So yeah, so it's a good question. So there are particular uses for Bell correlations, but more generally the idea of entanglement, which I talked about, is actually really the driving thing behind the future quantum technologies which Anil and Aria briefly mentioned this morning. So the idea of the ability to quantum communication, so to send information not faster than light, but to send information more securely. It turns out that entanglement can be useful to that, and for quantum computers, which is making use of the powers of qubits to do certain calculations much faster than any conventional computer could do, that also relies on entanglement. So these are things which are still in development, so I can't say that they affect our everyday life now, but in a few decades they may very well do. So science has this habit of people working out things just because it's interesting, and then down the track you find, oh wow, that's actually really useful.
아니 디와 당부된 세력 바이키랑서 능그 엔두스체 에네 타와 먼투니 데디 두스체 디키 에네 간소 고몽주 두스체 따든데 토니 디와 디겔라 랭커 게슬라나 아니 레스 세력 세드 카레스 라빈베나 아니 고보보 왕진이 찌기 에네 셰샤와든데 타 쥐샤와든데 요마다스 제자 디메베 금진 때는 삼주낭도 나소 용기여레스 남주 삼주나소 용사 예베 금진 때네 안능 간소 야르게 도야 고급라기여레스 아니 대관한시다 제단 dus pazo samchu manda mangbo yewa den zo shedu den zam bango nyongpo chagi yor den ngazo di yewa de mashi ranshi res baran ju tsirik bi nanglo choba yo mare dongdo che chi dus dena digmar wastin zo mashi gu yor stiga nashi yewa di ki kepsan deres la so da yarge doya di yores Einstein koran ki ngema tsedu ngom rik bi deshi gyagdan de zo nawa do yo mar den yimbe ne ya koran ane bel ki tanda ane namsha di takji cheche ani thumdin thoya rayo mares kesi ko this rings deche ani thoya rayo bimbena chikchina ko samutaya dela ani gwa chi sigres dijikche ani thiwani wadi ani kherange tan jugdum sina ani conclusion khares ya shdo chezada di kolla mune nge tanda sigme sani 제동 감직비 나로 런데시 작다 망부 요레 데시 작다 망부 요와 된조 아니 nga sani 아니 ngarang langjo khariemeda dinrekton 아니 sani kechesigis 아니 펜도 khariorese ektewa jorada thanda시 펜도 단지 아니 제동 감직비 펜도 khariemeda zo arieda kunjuk 망부 shesos nizu 아니 파조 다 웰리 뉴로 땅투 요레 시기요 마르테네 파 땅비임베나 고마쇼레다 dinrek nyinga chungwa 아니 대한나시 아니 컴퓨터라 소와 kunjuk 지 코용두 sambal라 thandek 지 코탕레 아니 지 kortuvya dindeki pendo yungu yores cheza ta pendo shevi imbana shezo yomares
다 단다 상황 주고 요도 아니
ngarang ke tol chik shu choba chirwa. Tanda nge tarang chawa tso de nge tarang shua yin yin tanda nge su pendo yume kol chik kame chung suwa. Ti yundu ta chik tsari da ane nga zu di technology yaje chenpe ke pendo katse chung yume de tanga nga zu shira she mogoba chires. Ti shira ke pendo chebo pena tarin bon dunde che kuku yone re ka yine re shibu chung yores. Ina ya ta digi tsari yaje chenpe de neba kar chung yores. Ti kaya sungumad was. Pena tsari yaje chenpe ke nyele la tena dunjen chon cha chik yunan zambuli cheka torshi tanya ki ene tsari ki yaje chenpe ke chungde cha yores. Pena zambuli nala tanda Korea ke mi tirgo tela zambuli sheko kudu was. Ti sheko jumsen khares kuy lakwa dunjen chon cha tsari pe suyo shabe chala ji kuy lakwa yoza ti chik lego yores. Ti maase pa tensan zambuli nala ya ngele meba nasa mambuchi lego yores. 나자 대야 폐제 체리기 제제로 차기도 고스 아니 체리빠디 람데 쟁인다고 차기 얼마 체리빠디기 리빠디 야고절 배주 땅한 체리비 라발 데민도스 가르스나 체리빠디 레바 배주 땅바디 총바디주 주칭바디주 배주 땅아지네 에는 정보리 왕줘야 아니 밀이야 뭐야 삼 말아야 되는 사초야 통 말아야 되는 통 줘야 나자 매번 나자 소야 답변은 나자 직 수업이나 아니 대매 송에게 매일 총자 암지 사발래야 텐제기 배때 세리기 야가 도안이 지고 때에나 가제지 전환 수상고도 아니 배나 세리기 시부제게 야제 여보 땅 투구요나 아니 줄롱바 매쇼에 갈래 지게 밤도 지자면 매세토야 출로 주고는 초가도야 대마시게 lumba jobe na tende chanja chu ne norgi charba jaya done tende ge che the yor bes kharesna manzu tanda cheri da nangbe chu ni keje kame nang yor was 제도 산지의 숭대 토마 개와 파르도 개마 타마 개와세 산지의 숭어버티 개와지 마도 되게 먹게와 지게 레부촌 토야요 말스 제네 토야요 말스 티인도 디세리기 자베 낭베기 추인의 파 오종 제하다 파 코란솔이 폐한 그 다시 제르마 세리기 추 낭발 추블라야 케멘타 이게 동민도스 된 텔레렌지 나오나스 What I was saying was that because the scientific progress has given us very much, science and technology development has given us a lot of comforts and requirements. At the same time, there is a lot of negative developments, such like nuclear and neutral bombs. All these are destructive. At the same time, the scientists, whatever the discoveries you make it, you are not in a position to use it for positive purposes, but you have been used, your knowledge has been used by the business people, commercial people, they use it. At the same time, they make a lot of different productions, which is very harmful to the health. Whatever we consume today, all are pesticides, all are poisoned. So every day, the people suffer because of the scientific discoveries, I should say. So, in other words, I was saying that can you make such a bomb, a wealth bomb, that you can throw in Africa and Nigeria, anywhere, when there's people are starving. Instead of throwing the nuclear, neutral bombs to destroy the world. So what I was saying, the Buddha was teaching is never been negative. Everything is positive from beginning to end. And even this most important, like mobiles, even we have a lot of negative feedbacks here. If you can't keep it near your bed, near your pillow, you should keep a distance. Even when you charge, you can't use it. And for instance, recently I have information saying that India, normally they used to have ocean salt, that is natural salt, is very good. But then the present Tata salt is very bad for the health, and it brings us a lot of negative sickness. And because of that, many doctors and the business people, they are making money. So how you scientists use it for more purposeful
So
ones.
Ian is going to try and answer something. Ian, keep it short.
All right, I'll keep it short because everybody wants their tea. But so I actually agree with much of what you say, and I try as a scientist very hard to teach my students that some of these things. When I teach nuclear physics, I always stop and I talk about the atom bomb, and I make a point of telling them exactly how many people died. I think what a lot of this is happening is that there's human nature involved in this, because humanity has a tendency to exploit things for the worse regardless. I think one of the things that we can do as scientists is we can try, as I try to do, to focus our research in a way, as much as possible, in a way that can benefit society. And I try to do that, and I teach at an institution that is a religious institution. It's sponsored by the Catholic Church, so our students have to take ethics and philosophy and theology classes. And we try to make sure that we tie all of that stuff together so that we give them the moral, how do I put it, the moral grounding to make the right decisions. I don't think it would be right. I personally don't think it would be right to give up on science, because I think science has given us a lot. I think what we have to do is we have to proceed cautiously, and I think we have to proceed in such a way that we recognize that there has to be there are a lot of problems in the world that need to be solved. Not the least of, and probably the biggest of which is that business exploits this and people end up losing in the end, and that is definitely a bad thing, and we have to find a way. And I don't know if we're doing a good job or not. There are literally thousands of scientists around the world, so it's very difficult to say in general. But I know that I'm trying very hard, and I know a lot of my colleagues are trying very hard to work on projects that do benefit society, so that some of what we develop is going towards helping people. And it's something I believe very strongly in. So we're working on it.
Thank you.